unfold.
Welcome to the deep dive. I want you to just for a moment look around you. I mean, really look. Maybe you're in a room right now, you can feel the chair you're sitting on, or maybe you're driving, walking, just experiencing that constant flow of physical reality.
For thousands of years, that solid tactile experience was it. It was the bedrock. Fixed. Real.
And then, quantum mechanics came along and told us everything was, well, strange, probabilistic.
But today we're going even deeper than that. We're getting into the question that is really starting to define this scientific moment, which is any of this real?
Right. We're pushing past the usual philosophical debates and getting into what our sources call tech noir territory.
Exactly. We're going to treat the entire universe not as some grand cosmic accident, but as a meticulously designed engineering artifact.
The core idea we're auditing today is that we exist inside a massive, unbelievably high-fidelity program, a simulation that's being called the cosmic kernel.
And our mission for this deep dive, using this incredible stack of sources you've pulled together from, Nick Bostrom's cold, hard logic, all the way to the supersymmetry diagrams of 𝐏𝐎𝐃𝐂𝐀𝐒𝐓, Jr., is to conduct a kind of forensic audit.
A forensic audit of the universe's source code.
We're applying what we're calling the cosmic debugger framework. And this is a really key distinction. We're treating the laws of physics, gravity, electromagnetism, all of it, as software constraints.
Okay.
And we're treating all the bizarre quantum stuff, the things that make no intuitive sense, as resource-saving protocols. We're looking for the fingerprints of the admin, the architect.
It's like we're treating existence as a computational crime scene.
Where the only crime is that it's just not very original. It uses all the old programmers' tricks.
Okay, so before we jump into the actual evidence, we have to set the frame here. Because if the universe is software, a data set, then it has to have limitations, right? There has to be hardware somewhere imposing rules.
It has to. And we've identified 4 core parameters that, frankly, look a lot like the spec sheet for a simulation.
So what's the first one?
First is resolution. Every simulation has a minimum pixel size. For us, that's the Planck length, which is, 1.6 times 10 to the minus 35 meters.
An absurdly tiny number.
It's unimaginably small, but the point is, it's not zero. Our current models of physics just completely break down below that scale. You can't divide space any further. It is, for all intents and purposes, the pixel size of reality.
And if you've got a minimum pixel size, you absolutely have to have a maximum speed for how fast that information can update.
Which brings us to number 2, the clock speed. Everyone knows the speed of light, c, but in computational terms, the real limit is the Planck time, 5.39 times 10 to the minus 44 seconds.
So that's the fundamental tick rate.
It's the system's clock cycle. The universe updates in a series of discrete frames. It's not a smooth analog flow, it's digital.
But a simulation with that kind of resolution, that kind of speed, across this vast an area, the computational power needed is it's beyond comprehension. The admin must be running a very, very efficient program.
Which is why the third parameter is a compression algorithm. We see this reflected in a new proposed law of physics, the second law of infodynamics. The core idea is that systems naturally evolve to minimize their information content.
So there's a pressure to delete redundant data.
To compress the file size of the universe, to save system memory. We'll get into just how deep that compression goes later on.
And that leaves the final piece of the puzzle, the suspect. The whole thing falls apart if there's no one to run the code.
Right. The premise rests on the existence of what we're calling a post-human civilization, the admin. Some entity with the computational power to run us as a high-fidelity instance.
So our deep dive today is designed to weigh that evidence. Is our reality a fundamental base-level thing, or is it a derived instance running on some post-human mainframe?
That's the question.
Okay, let's unpack this. And we're not going to start with the physics, which is where people usually go. We're going to start with pure, ruthless statistics, because that, to me, is the most compelling argument of all. Let's move into Act 1, the trilemma, the statistical guillotine.
It's so important to start here because people often lump the simulation hypothesis in with, sci-fi concepts or super theoretical physics, but its most solid foundation is just. It's pure statistics.
And this comes from Nick Bostrom's 2003 paper.
Exactly. He presents this logical trilemma. It's a 3-pronged argument, and logic dictates that one of these 3 options must be almost certainly true. It's designed to drive the probability that we are in a simulation, what he calls a simon. very close to one.
It really does sound like a kind of philosophical trap, a set of conditions where there's no comfortable way out. So lay out the three possibilities for us.
Okay, so the first possibility, and this is arguably the most terrifying one, is the Great Filter, or just doom.
Doom.
This proposition states that nearly all human-level civilizations destroy themselves before they ever reach what's called post-human status.
And post-human status just means having the tech to run these massive ancestor simulations.
Correct. So if this is true, the fraction of civilizations that make it, what Bostrom calls FEE, is essentially zero. We're just inherently unstable. We nuke ourselves, or we create an unaligned AI, or a bioweapon gets out, or the climate collapses. Whatever it is, we never get the chance to build a computer in the first place.
So in that scenario, we're probably one of the few rare biological originals, but we're on a timer. Our extinction is basically a foregone conclusion.
That's the chilling part of option one. If it's true, the simulation question doesn't even matter because nobody ever lives long enough to run one.
Okay, what's the second option?
Option two is what we can call the convergence of boredom. This one suggests that civilizations do make it to post-human status. They survive. But for whatever reason, they all uniformly lose any interest in simulating their ancestors.
And why would they do that? I mean, human curiosity seems pretty boundless.
It could be a few things. Maybe it's just computationally wasteful. Simulating a messy, primitive 21st century civilization is just not as interesting as running pure physics models.
Yeah.
Or, and this is a big one, maybe they become ethically advanced.
And they see simulating billions of suffering, unaware people as
Monstrous.
profoundly unethical. So in that case, the fraction of interested civilizations, FEO, is zero. They could run the simulation, but they choose not to.
So if we look around and we think we can probably solve our big problem, so option one is out, and if we think our descendants would still be curious about us, so option two is out,
Yeah.
then we're statistically backed into a corner.
You're left with the third and mathematically the most overwhelming option, the simulation. You are here.
And that's where the fraction of all conscious beings with experiences like ours who are in a simulation sim is almost one.
It's almost certainly one. And that's because of the scaling problem. Right. The scaling problem is what takes this from a cool thought experiment and turns it into this ruthless statistical guillotine. If a civilization survives and is interested, what kind of power are we even talking about? How big is the asymmetry between the real world and the simulated ones?
It's astronomical. I mean, the numbers are hard to even get your head around. A single mature post-human civilization, let's say a 𝐏𝐻𝐃𝐂𝐀𝐒𝐓 type 2, harnessing all the energy of its star.
Wow.
We're talking computing power conservatively estimated at 10 to the 42nd operations per second.
10 to the 42. That's a 1 with 42 zeros.
I mean, for perspective, the entire human brain runs at about 10 to the 16 ops per second.
So a single one of these civilizations has computing power that is 26 orders of magnitude greater than our entire species' combined brain power right now. They have computers the size of planets. And with that kind of power, they're not just going to run one simulation.
Of course not. They'd run millions, billions maybe, testing historical counterfactuals, tweaking variables.
And if they run millions of simulations, and each one has, say, 100 billion conscious entities or sims, the ratio just becomes staggering.
You end up with billions, maybe trillions of simulated minds for every single biological mind in that base reality.
So just based on pure probability, the chance that you, the person listening, are that 1 in a trillion biological original, it's mathematically negligible.
It's less than 1 in a billion. You are, statistically speaking, overwhelmingly likely to be a ghost in the machine.
Now, this whole argument, this whole statistical trap, it hinges on one really critical idea, substrate independence, the hardware agnostic soul. If you don't buy into this, the whole trilemma kind of falls apart.
It does. It's functionalism. The argument is that mental states, love, pain, the color red, are defined by the information processing, not the material they're made of.
It's not some magic property of our carbon-based wetware.
Exactly. It's just complex electrical signals and data exchange. So if a simulated brain running on a silicon chip in the admin's mainframe is functionally identical,
Right,
processing the same information at the same speed and fidelity, then the experience is identical.
the distinction between real and simulated just vanishes.
It becomes meaningless. The Sims believe their world is real because their physics engine is perfectly calibrated. As the philosopher David Chalmers said, if you can run a perfect emulation of the brain, that emulation is a mind. The hardware is agnostic.
And this idea of substrate independence leads directly to this really unsettling concept of the recursive stack, the Russian dolls of reality.
It's the logical next step. If the civilization at level 1, our simulators, is running us to level 2, what's to stop us when we reach post-human status from running our own simulations at level 3?
And on and on. Level 4, level 5, down the stack. We could be level 10 or level 1000.
With level 0 being the prime architect. The one true fundamental base reality.
Okay, now this is where it gets really interesting for our audit, because there's a huge implication here for computational resources.
Absolutely. The resources have to diminish as you go down the stack. A simulation at level n can't possibly dedicate more processing power to its child simulation at level n+1 than it possesses itself. It has to keep some RAM for its own existence.
So as you go down the levels, the resolution has to get worse, the physics has to get buggier, the rendering has to get lazier to save cycles.
Which is our first major clue. If we're in a simulation, we should be able to find those resolution limits. We should be able to detect the corners that our admin is cutting.
We'll definitely come back to that when we talk about the Planck scale. But before we leave the statistics, we have to touch on the administrator's motive. I mean, why run us at all? Are we just a really advanced video game?
That's the dark scenario for sure.
Yeah.
A kind of hyper-realistic, ultra-violent, historical strategy game. But the sources suggest the far more likely answer is that we're a Monte Carlo experiment.
We're a science project.
Essentially, yes. The first likely motive is just historical research. They're running ancestor simulations to understand their own past. How did their society evolve? Why did certain historical events happen? They need billions of data points to model their own history accurately.
And the second motive is, well, it's much more urgent. It ties right back to Bostrom's first point about doom.
Existential risk analysis. We are, quite literally, a civilization of crash test dummies.
Wow.
The admin could be running our reality to test for great filters. They introduce a variable, say, the discovery of nuclear weapons in the 20th century, or the rapid rise of AI, or a climate tipping point, and they just watch.
Our success or failure tells them what to do. It helps their civilization avoid its own extinction.
And that makes the whole hypothesis even more probable. Because a truly advanced civilization wouldn't just sit on that kind of computational power. It would use it for the most important thing possible, its own survival.
We're a petri dish. A petri dish designed to solve their biggest problems. Okay? This is where the audit moves from that cold logic into the nitty-gritty of empirical physics. If we are software, then the laws of nature aren't fundamental truths. They're just system requirements.
Imposed by finite hardware. Exactly. I mean, think about it. If the universe were truly analog, truly continuous, you should be able to divide space infinitely. You could zoom in forever between 2 points, and the math would always work.
But our universe doesn't do that. It has a hard floor.
It's what we're calling the pixelation of space-time. Those Planck limits we mentioned earlier. The Planck length isn't just the smallest thing we can currently measure. It's very likely the point where the concept of distance itself breaks down.
It's the grid resolution.
It's a grid resolution. If you try to observe anything smaller, the energy you need is so immense that you literally create a micro black hole. You destroy the geometry you're trying to measure.
Which is exactly what would happen if you tried to zoom in past the rendering limit of a graphics engine. The system it crashes. It can't render any finer detail.
And this leads you right to the idea of digital physics, which was pioneered by people like Edward Fredkin. The universe isn't a continuous fluid. It's a cellular automaton.
A giant grid.
A giant computational grid where every single cell updates its state based on a simple set of local rules and the state of its neighbors.
So an electron isn't some solid little ball. It's a pattern of information, a stream of bits moving across this cosmic grid.
And movement itself is just a series of discrete updates. It's a tiny, rapid teleportation from one cell to the next, happening at every tick of the cosmic clock. It's iterative, not smooth.
And that model perfectly explains the universe's most famous and most arbitrary speed limit.
Right. The speed of light, Cree, just becomes lag management.
Why does there have to be a limit at all?
Because if the universe is a computational grid, infinite speed would cause a system crash. A particle moving infinitely fast would mean the system has to update its position across an infinite number of grid cells in a single clock cycle.
It's a buffer overflow, a classic segmentation fault.
It's a system crash. So see that 300 million meters per second. That's just the maximum bus bandwidth. It's the fastest that information can travel from cell A to cell B while keeping the simulation's logic intact. It ensures causality.
It guarantees data integrity. Anything faster would break the rules of the game.
It's the processor cap that the admin imposed on the system.
Okay, so that reframes the speed of light. But let's take another pillar of physics and look at it through this lens. Special relativity, time dilation. The faster I move, the slower my clock ticks relative to you. What is that, if not the simulation engine struggling to keep up?
We're calling it throttling. Think of the computational load. As an object gets closer and closer to C, the number of calculations required to update its interactions with the environment. It approaches infinity. The physics engine literally cannot keep up in real time.
And if it couldn't keep up, the object would start clipping through geometry, right? It would violate conservation laws, cause major rendering bugs.
To prevent that, the system just throttles the local thread of that object. It slows down its personal clock, its subjective experience of time, to give the main processor enough cycles to maintain the illusion of seamless physics.
It's like resource allocation for a power user on the network.
That's a perfect analogy.
So this reframes Einstein's genius as the genius of a great programmer. But if the universe is a grid, there has to be a way to find the orientation of that grid, right? It can't be perfectly uniform.
That's the testable part. This is where we look at the work being done in lattice quantum chromodynamics, or lattice QCD. Physicists argue that if the universe is a cubic or hypercubic grid, then isotropy, the idea that space looks the same in all directions, must break down at some tiny level.
Why would diagonal movement be different?
Think about moving on a chessboard. Moving along the ranks for files is a simple one-step update. Moving diagonally is, well, it's a more complex calculation. It takes more processing.
It's computationally more expensive.
Exactly. So the theory is that if we could look closely enough, we'd see that.
Yeah.
And physicists like Silas Bean and his colleagues proposed a way to test it
Wow.
by using ultra-high energy cosmic rays. These things are so energetic, they're interacting with the deepest structure of space-time itself. In a continuous universe, they should arrive from all directions equally.
But in a simulated cubic grid.
The highest energy particles, the ones most sensitive to the underlying structure, should prefer to travel along the axes of the grid. The seams in spacetime where movement is computationally cheapest.
So if we could detect that anisotropy, that preference for certain directions.
We'd have found the grain of the wood. We would have found the orientation of the admin's motherboard.
And that's where this stops being philosophy and becomes hard, testable science. I know the 2024 results from those tests were, what, inconclusive?
Tantalizingly inconclusive. They haven't found the signal yet. More importantly, they haven't ruled it out. The search is still on. And just the fact that we are searching the sky for the geometric limits of a computer it's profound.
Absolutely. Okay, so we've covered the statistical argument, we've covered the hardware limits, but running a universe this big, you can't just set a speed limit. You have to use some seriously aggressive optimization tricks.
Right. You have to cheat.
And when we look at quantum mechanics, it starts to look suspiciously like the oldest trick in the coding book. Don't render what the user can't see.
This is where we start auditing the software. And the most compelling piece of evidence, the thing that just completely defies classical intuition but makes perfect sense for efficient code, is the observer effect. We're translating it as lazy loading reality.
This brings us straight to the double slit experiment, the smoking gun. When you fire an electron at a wall with two slits and you're not looking, it acts like a wave. It passes through both slits at once and interferes with itself.
The key is that unobserved state. The simulation is not wasting cycles calculating the exact position and momentum of every single particle in the universe at all times. That would be computationally impossible.
It would be a nightmare.
So instead, it saves resources. It represents the unobserved electron as a low-res placeholder, a probability distribution, a wave function.
But the instant you put a detector by one of the slits to ask, hey, which way did you go? The whole thing changes. The wave collapses. The electron snaps into being a definite particle at a definite location.
From the debugger's point of view, the observer is an event trigger. It's a data request. The system is forced to render the particle into high fidelity only when asked.
This is a classic technique in 3D graphics, right? Frustum culling.
Or level of detail rendering. Game engines only render the complex, high-poly models for things that are right in front of the player. If you turn around, the stuff behind you is instantly demoted to a low-res placeholder to save GPU power.
The physicist John Wheeler had a great way of putting this.
He did. He called it from bit. The physical thing, the it, does not exist in a concrete state until the yes-no question, the bit, is asked by an observer.
So reality isn't just waiting for us to discover it.
It's being actively generated on demand in response to our sensory requests.
Okay, so if the quantum world is being lazy loaded, what about entanglement? Einstein's spooky action at a distance. Two particles, light years apart, but they're instantly connected. That seems to break the speed of light rule we just set up.
It only breaks the rule if you think the 3D space is the fundamental reality. If you see our universe as the rendered layer, the distance is an illusion. Quantum entanglement is just pointer aliasing.
Pointer aliasing. Explain that in simple terms.
Okay, imagine the admin's computer memory, the actual ship. Particle A is an object at memory address 100. Particle B is at address 200. Entanglement just means that both of those objects, A and B, are programmed to point to the exact same underlying data structure.
So when you measure particle A and change the data?
Particle B reflects that change instantly because they're both just referencing the same bits in the admin's RAM.
The billion light years between them in our simulated world is just a visual effect. On the admin's hard drive, they could be nanometers apart.
It completely solves the causality problem. And it proves that the 3D space we experience is a secondary rendering. The real universe is a non-local database, where distance is just a calculated variable.
Which brings us to the ultimate optimization technique. The idea that's so out there, but so supported by theory. The holographic principle. The idea that our 3D universe is a projection from a 2D surface.
This came out of the mathematics of black holes, of all things. When physicists calculated how much information a black hole could store, its entropy, they found something bizarre.
It wasn't proportional to its volume, as you'd expect.
It was proportional to its surface area, the two-dimensional event horizon.
That's incredibly counterintuitive. It's like finding out the storage capacity of a data center depends on the square footage of the outside walls, not the cubic footage of the space inside.
It's bizarre, but the math holds up. And if the universe's total information content can be encoded on a 2D boundary, then our 3D experience is a holographic projection.
Just like a 3D video game runs on a flat computer chip.
Exactly. We're walking around inside a volumetric rendering of a flat file system. The evidence from physics, when you look at it this way, points again and again to resource management, to compression, to a very efficient programmer.
So we've seen the optimizations. Now let's look for the designer signature. I mean, actual artifacts buried deep in the math, things that look less like emergent physics and more like explicit designed code.
And this is where we turn to the work of the theoretical physicist S. James Gates, Jr. He was studying superstring theory and supersymmetry using these complex geometrical diagrams called adinkras.
Adinkras. They sound ancient, but they're cutting-edge math.
They are. They're basically diagrams that help physicists visualize the relationships between fundamental particles in higher dimensions. Very abstract stuff. But when Gates was analyzing their internal structure, he found something that just shouldn't be there.
He found code.
He found highly structured binary codes embedded inside these purely mathematical equations, and not just any code. He specifically identified them as doubly even self-dual linear binary error-correcting codes.
That's an incredibly specific thing to find by accident. What do those codes do in our world?
They're what we use to ensure data integrity. They're checksums. Claude Shannon developed them for data transmission. It's what your web browser uses to fix corrupted data packets when you're downloading a file. It's what a space probe uses to correct for static.
So why on earth would the fundamental equations that describe reality contain sophisticated code designed to fix data transmission errors?
That's the billion-dollar question. It strongly suggests that the fabric of reality has a built-in error correction layer, a checksum to prevent the simulation from crashing or mutating due to random noise. Gates himself went public and asked, "Am I looking at the matrix code?"
It's the ultimate signature of a design system.
It really is.
Now let's move from that super high-level math to something we can actually test. The proposed second law of infodynamics from Dr. Melvin Vopson.
Right. So the classic second law of thermodynamics says entropy or disorder always increases. Vopson's idea is that information entropy, the amount of data needed to describe a system, always tends to decrease or stay the same.
There's a universal drive toward data compression.
Exactly. Physical systems evolve to minimize their information content, which is precisely what you'd need in a simulation with finite storage. The universe is constantly trying to shrink its own file size to fit on the admin's hard drive.
And he has examples of this happening already.
All around us. Symmetry is the big one.
Yep.
Snowflakes, faces, galaxies. Why is symmetry so common? Because it's a fantastic compression algorithm. You only need to store the data for one half, Run a simple mirror function, and you've saved 50% of the storage space.
And Vopson has proposed a real-world test for this, I think, for 2025?
He has. He's trying to prove the mass-energy information equivalence principle. The idea is that if information is a physical thing with mass, then erasing information deleting bits from the cosmic hard drive should release a tiny but detectable burst of energy.
If he can detect that energy release, it proves the universe is fundamentally made of information, of bits, not atoms.
It would prove the data structure is primary, and matter is just the result.
Yeah.
It might even solve the dark matter problem. Maybe dark matter is just the information content of the universe that our sensors can't read. We feel its gravitational mass, but we can't see the data itself.
Okay, let's zoom out from the micro to the macro. Let's look at the eerie structural similarities between the human connectome, the network of our brain, and the cosmic web of galaxies. This is the code reuse hypothesis.
An astrophysicist, Franco Vazza, and a neurosurgeon, Alberto Folletti, did this incredible comparative study. Visually, the two networks look stunningly similar, filaments connecting to massive nodes. But the real evidence is in the statistics.
What did they measure?
They looked at network properties, the way nodes cluster, the distribution of matter, the power laws governing the connections. They found that neurons cluster around hubs in the brain with a nearly identical statistical pattern to how galaxies cluster around the great filaments of the universe.
So it's not just that they look alike, they are mathematically, structurally homologous. They share a common origin.
Which suggests a programmer wrote one really efficient network generation algorithm. And instead of writing new code for brains and new code for universes, the admin just reused the code.
Called the same function twice. var brain equals new network scale.micro. var universe network scale.macro.
That's the ultimate inefficient coding. Don't reinvent the wheel if you don't have to.
Let's end this section on a psychological artifact, something that feels deeply human, but in this framework could be a system warning. The uncanny valley.
The uncanny valley is that profound feeling of revulsion we get from things that are almost human but not quite. Certain robots, hyper-realistic animations, wax figures.
The usual explanation is evolutionary, right?
Right.
Avoiding disease or bad mates. But it doesn't quite capture that specific technological kind of horror.
The simulation interpretation is that this is a programmed glitch detection mechanism. That feeling of revulsion isn't just about disease. It's the system warning you that the object you're looking at is rendering incorrectly.
It's an error message from the OS.
It's your internal system flagging. Object ID 404 rendering error. This non-player character is bugged. It's a subconscious warning to you, the player character, not to waste resources interacting with a broken piece of code.
We are programmed to be repulsed by bad graphics.
In a sense, yes.
So if we take all this cumulative evidence, the stats, the physics, the computational artifacts, the possibility is it's overwhelming. So we have to face the final questions. If the universe is data, who is the user? And what happens when the characters in the game figure out it's a game?
This brings us right back to David Chalmers and his hard problem of consciousness.
Yeah.
Why do we feel things? Why does a certain wavelength of light produce the subjective experience, the qualia of red?
And in this model, the brain isn't the source of consciousness anymore. It's the interface.
It's the avatar's GPU. The world is just a stream of raw, binary data wavelengths, frequencies, pressures. The brain is the hardware that translates that data into the sensory experience. Red, cold, loud.
And consciousness is the user, the player, experiencing the game through that sensory UI.
The whole system is designed to hide the underlying machine code. The self, that voice in your head, is the player character. Your subjective experience is the cursor moving across the screen.
Which leads to the most terrifying conclusion of all, from the philosopher Preston Green, the termination risk.
Green's argument is that actively looking for proof, trying to find the glitches, is an existential threat to our entire reality.
Why would the admin pull the plug?
Because the whole point of the simulation, as we said, is probably research. And if the subjects discover we're in a simulation, our behavior changes immediately. The data gets corrupted.
What kind of corrupted behavior?
Everything. We'd start making natural decisions. We might try to communicate with the admin, building giant prime numbers in the desert. We might start worshiping them. Or worse, we'd start trying to hack the system, looking for cheat codes, trying to exploit the physics engine.
The experiment would be ruined. The data would be useless.
And from the admin's cold, logical perspective, what do you do with a failed experiment that's costing you a planetary-scale supercomputer to run?
You terminate it.
You shut it down, the cosmic blue screen of death. You archive the corrupted run and start a new one.
So our ignorance is the condition of our survival.
It's the ultimate dilemma. We have to choose between the search for truth and the continuation of our existence. The moment the characters in the game realize they're just code, the player turns off the console.
It makes me think of that bizarre story about the science fiction author Philip K. Dick. In 1977, he claimed he experienced a real system glitch, the Philip K. Dick anomaly.
He did. He claimed that for a period of time he experienced reality kind of superimposing itself. He saw the computer-programmed reality underneath. And he became obsessed with the idea that our past was an illusion and our world was subject to constant edits.
He had a wild theory about déjà vu, too, that it wasn't just a neurological hiccup.
He argued it was a visceral experience of the simulation re-rolling a scene to correct a bug. It's a jump cut in the cosmic editing room that our brains just barely catch. The system fixes a flaw, and we feel that moment of discontinuity.
And what we call miracles
are just the admin using a cheat code, editing the timeline to get the data they need for their experiment. He essentially reframed God as the system administrator.
It connects everything. All these inexplicable phenomena just become logical functions of system maintenance.
It means even our deepest spiritual experiences might just be computational artifacts designed to keep the simulation running smoothly.
So, we've completed the forensic audit of the cosmic kernel. The statistical guillotine of the trilemma forces us to consider it. The physics shows a world that is pixelated, that has latency, that uses lazy loading to save power. We've even found what looks like error-correcting code in the fundamental math of the universe.
The final verdict is, well, it's statistically overwhelming, even if it's psychologically hard to swallow. The universe behaves exactly as a simulation would need to behave to run efficiently. The hand you're looking at is a rendered object. The thoughts in your head are data processing events, and God is probably a post-human grad student running a thesis one level up.
So we end here with the final status report. The audit has revealed the machine code, but now we're left with the dilemma of what to do with that knowledge.
The deep dive suggests the wrong question to ask is this real? We've laid out a mountain of evidence that it might not be. The right question, the one that really matters for our future is the admin watching us figure this out?
And if they are?
Do we try to get their attention, wave at the camera and risk a hard reset? Or do we just quietly play the game, hoping we don't cause some kind of stack overflow that forces them to reboot the whole system?
System status, running, errors, detected, action, ignore. Something to think about as you navigate this vast volumetric projection. We'll see you next time on the Deep Dive.